Okay, so in this video I wanted to go over nuclear chemistry, just pretty random. And nuclear chemistry is one of the most interesting sections of chemistry I find, along with organic chemistry and also electrochemistry. They're very interesting to see how they work, especially nuclear. Nuclear is used often for weapons of mass destruction and is also used as a source of nuclear power. Also in stars, they use nuclear energy to gain energy and feed. So for nuclear chemistry, we're always going to start with the nucleus because that's nuclear to nucleus, yeah. And we know the two particles inside the nucleus, the subatomic particles, they're called the protons and neutrons, right? So proton and neutron, and that's what's in the nucleus. In the outside, we have an electron cloud, which contains electrons, right? And we know protons have a +1 charge and neutrons have no charge. The entire structure of an atom is rearranged to achieve more stability. That's usually always the goal of an element, to achieve stability. Whether it's trying to achieve stability through bonding and then trying to gain all the electrons it can to reach that ideal state that neon, argon, and krypton are on, um, or it's cutting itself basically by radioactive decay and emitting particles in order to reduce to a more simplified state, to not have that many neutrons, to just become more simple. And generally, it's the elements after number 84 or 83 that tend to be more radioactive. We call this also a transmutation. That's when you go from one element to another. And because the nucleus of the entire element will be rearranged, then it can form actually a new element. So it's new element basically. The laws of conservation and laws of energy and whatnot that we had in chemical reactions don't really apply here. This is more intense to be drawn for that. So basically we have a group of particles that are emitted, that were found out to be emitted from radioactive isotopes. Clear. And one of them is alpha, which is actually a helium nucleus, interestingly enough. And this is the notation they use. The 4 is like the mass number, and the 2 is the number of protons and number of electrons, which is also the atomic number. And then beta, or it goes something like that. Beta particle is just an electron, but it's not gained from the electron cloud. I'll go over that. And this is the notation, because 0 charge and -1 atomic, basically. We also have positron, which is like this electron but positive, so like 0 plus 1 e. We also have gamma, which is y, and then 0 0. It's usually neglected because it has no charge and no mass at the same time. So we also can have electron capture, which is actually one of the more interesting ones. So these radioactive elements can also be called radioactive isotopes. So radioactive isotopes. Right. Um, so we'll start with alpha decay. So we know an alpha particle is really a helium nucleus. 2He. And we have certain elements listed on a a table also which ones will undergo what type of decay. It's in your best interest to try to have it memorized or use a table if you have to. I want to use an example of what happens to francium Fr 220. 220 denotes the mass number, by the way. So it would be like francium 220 here, and then its atomic number is 87, and it becomes the helium nucleus comes out from it, right? The alpha particle is being emitted from it, so it has to be on the right side. And then plus 85, 216, AT. You see, the reason that this became 85 and 216 is because 2 plus 85 yields 87, and then 4 plus 216 is the same as 220. So all of these, the top and bottom, add up to each other eventually. And that's how you can find out what this is. If they just say like X is here, and then they give you this number and this number, then, well, you know that this and this would have to add to that, right? And you can always check. But basically, the atomic number decreased. So atomic decreased by 2. And then the mass also decreased by 4, though. Okay. And then we're going to do beta. Beta. Now, a beta particle is just an electron, really, like I was saying. That. And it actually comes from the nucleus, interestingly enough, not the electron cloud. And the question is why? Well, it results from the conversion of a neutron into a proton and then into an electron. So something happened like this. 1 N denotes neutron, and then 1 P plus -1 E is what happened. And typically the ones that have a high neutron ratio are the ones that undergo this as well. And now we can do an example of nickel 63. Again, that's the mass number. So 63 over 28, because that's the atomic number of nickel, and I yields 63, 29 copper plus -1 E, right? It should be something like that, because 29 minus 1 is the same as 28. 63 goes to 63 because this is 0. So all what really happened was we increased the atomic number by 1. The reversal happens if we have a positron, by the way. But anyway, let's go to gamma radiation. So gamma is represented by a Y, 0. And it's not typically shown because no mass, no charge. Then we go to positron. Basically a positive electron. Just a strange thing to say. And it's the conversion of a proton to a neutron and then to a positron. So it's kind of a similar thing with the beta and the positron. Just kind of almost a reversal of it. And we have an example of potassium 40. 40 over 19K yields, well, for positron, because the other one, we know beta increased the atomic charge, right? So then in this, it has to decrease it, right? Because if I wanted to add the +1 on this side, then I would have to have something else that needs the +1 to get into 19. In other words, 18 plus 1, right? So it's going to be 18, 40 argon, actually. that happens. And then we check because, well, 40 and 40 and plus 0, okay. 19 is 18 plus 1, yeah. So this makes sense. And then we have electron capture, an interesting one. You'll see why I say it's interesting. It's the capturing of an electron from the energy level closest to the nucleus by a proton in the nucleus, which is, this is really strange, because you know how you have all your orbitals? Well, apparently it creates a gap in the vacancy in the orbitals unintentionally, and therefore electrons drop to lower levels, so they're gonna like drop to lower levels. In other words, energy is emitted, because whenever they drop, if you have light, light is really what happens when electrons drop to lower energy levels, the principal energy levels, and so it dropped. So we have X-ray energy that comes off because of this. In other words, let me show you an example. Polonium 204 plus this is the only time that this will be on the reactant side rather than the product side. And then 204 80. I think that's 83 plus X-rays. Yeah, because 84 minus 1, yep, that's 83. And then X-rays are actually made, so energy is on the right side. And the amount of energy produced whenever we have this sort of, or any reaction, we can say, well, E equals mc squared, right? Einstein's equation. I'm actually going to go through an example with you guys. C is equal to the speed of light, and m is equal to the mass converted, and E is equal to the energy. So if I have, let's say, 1 mole of U-238, which actually has 14 steps in its decay, which was very interesting to write. It takes a while, but it's well worth it. Decays to thorium 234. It says 5.0 times 10 to negative 6 kilograms of matter we have. That's our information. And so we're trying to find energy. Okay, no big deal. We plug in 5.0 times 10 to negative 6 kg, all times the speed of light squared, which is equal to 3.00 times 10 to the 8th m/s squared. In other words, E equals 5.0 times 10 to the 11th in joules. Energy is usually always measured in joules. And that is basically it for Einstein's equation. Now, we also have the difference between fission and fusion, which I will talk about really quickly. Fission, fusion. Fusion is what goes on in the sun. It requires high temperature and pressure in order to commence. It greatly has a lot of energy that is emitted. Fission is the one that we use in bombs and the one that we also use in nuclear power plants. Fission is very dangerous to keep, but it's a splitting of one large nuclei into two smaller, right? And then fusion is the one that forms the larger nuclei, right? And that's basically it for that. That's all we really need to know. Fission is the one we mainly use. And that's it for this video. If you have any comments, questions, feel free to subscribe. If you're confused, feel free to ask.